Going to be discussing our progress thus far on our surface lot occupancy solution that we've been working on for the past couple of months here. So my name is Trevor. I'm the team leader, and my focus thus far has been on software and also some communication aspects as well.
My name is Austin. I'm largely responsible for the sensor technology as well as some of the PCB design.
Jin Xiao. I'm mainly focused on the power for the system and also for the PCB design.
My name is Rafi, and I'm in charge of Team Spotify's data transmission and power solutions.
Hi, my name is Kelsey, and I was in charge of the LCD decisions as well as project management. So currently at The Ohio State University, the surface lots don't display the occupancy of the lot. So for vehicle operators passing by, they might pass by a lot thinking that there aren't any available spaces when in fact there are spaces there, or they might enter a lot thinking that there are spaces just to find that there aren't spaces available. So hunting blindly for a parking space like this is time consuming and environmentally unfriendly. So our goal is to display parking occupancy so passerby visitors can observe the number of available parking spots within a surface lot.
The customer needs since the PDR have not changed. They're still the same, with the number one priority being reducing the hunting time to find a parking spot. We would also need to display the occupancy in some form so that it is used in a user-friendly manner so that the passerbys can make a decision for themselves whether or not to choose a lot. And it also has to be reliable in the adverse conditions that Ohio presents. Same as the constraints, it has not changed much since the PDR. It still has to withstand adverse conditions in Ohio. Wi-Fi is not ubiquitous across campus. We also have to consider several power structures in the parking lots. And also we would like to avoid in-ground solutions. In addition to the constraints is team expertise and the project timeline so that they can help us narrow down our solutions. And then our stakeholders, CampusParc and Dr. Z are our main sponsors. CampusParc is the one that provides the parking and observes the parking at Ohio State. The Ohio State University is the one that provides the rules and regulations of parking. And the entire Ohio State community is directly affected by parking on campus area, faculty and students. We are also stakeholders in this operation. We're learning to take on this project. It's the first time we're taking on a large project, and we're learning through the process.
Okay, from those customer needs, constraints, and other things, we devised a requirement table. First off, we want to display the occupancy accuracy, and we don't want to display a false spot when there is none. So therefore, we would like to be around 90% accurate. Secondly, we need to display this information to the user in some capacity, whether that's a on-site LED display or using CampusParc website integration or a standalone app. The final system needs to be able to withstand inclement weather. Right now, we're going to judge that by using an IP scale. The final determination on that is yet to be set. It needs to be powered without any outside power. And really, the only ideal for that is that it is powered independently. And for the duration of operation, ideally, you would like this to work 24 hours a day. 5 days a week would be optimal, but 7 days a week is what we're going to shoot for, so that way there's not an interruption of service.
Okay, so now we're going to talk about some of the technical aspects of our prototype and final design thus far. So this is a block diagram of our general goal and overall idea of what our solution will be. You see the system of ultrasonic sensors. We have some different ideas about how we can avoid some of the common troubles in using ultrasonic sensors in a system in terms of length of car and pedestrian interference, that sort of thing. So we have some ideas, not fully worked out, but we have some ideas on how we want to approach that problem. And then, of course, you see the ESP32, which we'll get into later, and some of the power components, and also the LoRa communication method, that we're gonna talk about a little bit later as well. And so this is our level 1 prototype and block diagram. So this is what we have currently in our setup. See a similar system that we're working within. We have our ESP32, we have our ultrasonic sensors labeled here, our LCD, and then in this case, we're still being powered by laptop. But we have plans to change that. Just based on this prototype, this is what we're doing right now. And so here's some sort of dissected pictures of our prototype. You see the ESP32 here, the ultrasonic sensors, the LED. But this is what I'd rather show. This is sort of how the system would look set up in a mock-up. So same sort of idea. Bidirectional detection, that was our main goal for this prototype. And it in fact works in that way that you'd expect. Cars in both ways contribute to the overall count of a lot. So we have a video demonstration, but that you're here, we're gonna do the demonstration at the end, if that works.
Okay, so looking at that prototype without the cover is a little daunting. There's a lot of wires going on. Here is a schematic that shows all the wire connections from the ESP32 to our 2 ultrasonic sensors and our LCD display. Both of which were rather easy to wire as they only have 4 pins each. 2 of those pins on every one is your power and your ground. So information was easy to handle between those 2. And that largely went into the selection of those components. But next, I would like to talk about why we're using ultrasonic sensors. Really, when you use an ultrasonic sensor, it gives you back a distance value. And with that distance value, you can then turn that into an analog value of like a 1 or a 0, yes or no, and whether or not there's an object there, depending on a set range. For this prototype, we decided to use this HC-SR04 ultrasonic sensor. And the reason for that is there's a lot of open source knowledge out there for us to gain a base of how these sensors work and how to use the technology, as well as to integrate it with all the other components. This particular sensor is good for prototyping. It has decent resolution and it works up to 13 feet, which is pretty good for what we're doing. However, it's not very reliable. It's not going to withstand weather conditions. It's not going to withstand constant use. It'll burn out quickly, which is why I have a couple ideas for the final consideration for the ultrasonic sensor. This first one is from Balmer Electronics. It is a transceiver, so this part right here sends and receives. The advantage of this component is that its resolution is extremely accurate, down to 0.03 millimeters. And with that, the hope is that we could reduce the amount of error in the passing by of cars in the middle area of the road. We can get like a real exact measure. And my other consideration for this is this distance sensor by Musa Electronics. They're a German manufacturer. And the advantage of this one is that it is already weather resistant and waterproof.
The current microcontroller that we're using for our prototype is the ESP32 DevKit V1. It is practical for the final solution as well. It has built-in Wi-Fi, so it would not need to rely on the Wi-Fi at OSU. It also has Bluetooth accessibility. So if we wanted to access data from the ESP32, if we connected to the Wi-Fi server or the Bluetooth of the ESP32 module, you'd be able to gain access on the like how many cars are in the lot, which is the data that we're presenting. And eventually it is compatible with LoRa. LoRa is the long range module that I'll talk about after this. Eventually the ESP32 will be set at long distances away from each other, so they'll need a way to connect, and it is compatible with LoRa. It also has 40 GPIO pins, so it has great flexibility with working with multiple aspects in the system.
So we decided to use the LCD with the ITC adapter, and the reason for this is because that helped to simplify it when we're integrating it with ESP32 and HC-SR4 sensors. It helped create a 4-pin connection, which was really nice for us. It's also compact and ideal size, so there are 2 lines when the screen is lit up, and that's nice because we can just display Campus Park and then counting and then the car count. So that's all the space we need. We didn't necessarily need anything bigger just for our level 1 prototype. And then on top of that, it's low cost. So if this did break for some reason, we could replace it pretty easily for maybe around $5, which is exactly the budget we'd be looking for.
And as I mentioned earlier, for the final design, we plan to work with the RFM 95 LoRa transceiver module. Again, what this does is there's going to be an antenna attached to it, and that allows if they're going to be separate microcontrollers, they're able to communicate to each other, or they can communicate to a local data hub where the numbers will be stored and also can be sent back, so that for example, at Buckeye Lot, if someone's entering from here and exiting through here, it would -1 and add 1 at the same time.
So for the power, we decided to use a hybrid power solution. So because the hybrid solution can utilize the Ohio riser and sustains the longevity of the system, and they require low maintenance. So we will use the solar panel as a power source to charge the battery and then power the whole system. As you can see the picture, that the top is what we built, what we want to build. The top is a solar panel, and that is a waterproof box. The rechargeable battery can be inside. So here is the schematics for the power. So you can see the 2 pins, and it can be connected to the solar panel directly. And then it have a voltage regulator. It will step down the voltage to 5 volt. And the next is the charge module, the TP56. It can be charged the battery and power the ESP32, and then power the whole system. So this is a 3.7 volt battery we use for the prototyping. It's really reliable, and it can work in all weather, like super hot or extremely cold. So, and it will have less power leakage, and so it can guarantee that it have a longer work time. And it also have a long life. The battery can recharge around 500 times. And after that, the maximum capacity will drop dramatically. So after that, we maybe change a new one. So, and also it's a low price. It's really good for the prototyping. Yeah. So this is when we need higher power. For the prototyping, the first choice we use is to put several batteries together, like shown here in the circuit. So here is the charger module, and this is the dial, and this is the fuse. So the dial here is for the reverse current protection. So if you accidentally put the battery in the opposite direction, so the current will flow through the dial and blow the fuse. So it will protect the charger module. And in the real implementation, so we need a higher capacity battery. So we also need to change to a higher power solar panel. Yeah. So this is the TP4056, the battery charger module. So as you can see here, it have the USB connector. It can connect directly through the laptop to power this and charge the battery, and we can test easily. And it also can, this 2 pin beside the connector is you can connect to the solar panel. And the left LED is when you put will connect to the battery, it will goes on, and it's red LED. And when the battery is fully charged, the bright blue LED will goes on. So it's easy to detect the battery charging situation. So, and another benefit is it can charge the battery and power the system in the same time. So it's good for prototyping, easy to use and really convenient.
Okay, so now one of the features or maybe future plans that maybe isn't in our requirements table is to integrate with CampusParc website or the app, depending on how our prototyping and final implementation ends up looking like. Also, it depends on a lot of the lots. If we want to have Wi-Fi or cellular, if that's an option, this might be a more viable solution instead of an LCD or LED display. So I just one of the options that we're considering going forward. And so in terms of testing, mainly our focus is going to be on comparing first compared to existing solutions that have an occupancy level already for surface lots. So Carmack 5, Buckeye Lot, some of these things, that's ideally where we're going to want to test our early, I guess, in the real world systems. And so right now we have our current prototype, but this is the direction of some of the later tests that we'll need to conduct with the battery, solar panel, and also communication out in the real world. And then of course, making sure that the software holds up if we're changing around the hardware. That's something else we're going to want to test. And of course, the weather conditions given the entire setup. We don't know exactly how the hardware and software are going to integrate into the entire system. So making sure that, people aren't able to or wanting to kick things over or foot traffic, snow, all those things. And so this is sort of the idea of what we're going to want to do next semester. So this is Carmack, and this would be maybe the ideal place to test our early prototypes. There's already there's already occupancy detection for this lot, so it'd be great to compare our solution to what already exists, and that would help us debug and continue to improve, pushing towards a final solution that maybe works in or it's able to be tested in other lots. And this is the setup for the final design. This is what we're wanting to work out here. And so next we're going to talk about our project management and organization thus far.
So these are some of the milestones that we had created. In the beginning of the semester, we had a kickoff meeting where we were trying to come up with solutions for this project. We ended up spending a little bit more time on the research solution than we had planned, but we're going to learn from that next semester, which we'll cover a little bit later. But towards the end of the semester, you can see we made it to our level 0 and level 1 prototypes. And next semester we have plans. It is not displayed here, but after we get the bill of materials approved, we're going to start working on our level 2 and further prototypes. So this is for next semester as well, and we just have all of the steps that we're going to be taking, and sort of what Trevor was just talking about before. He sort of gave you the more detailed version of our plans for the level 2 prototypes, but we're going to have eventually a level 3 prototype with the LoRa module in it, and then we'll be able to build our final design ideally by the time of the presentation and report, and we'll be able to do a final presentation then based off of what we had sort of mentioned earlier. And then this scan chart is also broken up across 2 slides just for clarity, but this sort of covers all of the milestones and our progress with the milestones. So you can see with our research and problem definition, we've already completed all of those milestones. And then with the detailed design report, we're working on the chapters that have been assigned for this semester, and we'll continue to fill out that report throughout next semester as we make further developments. And then you can just see sort of our more progress that we plan on making with our future prototypes here. So we've met most of our prototype one goals for the semester, and then moving on to next semester, we have more goals that we plan on finishing out as displayed there. And then these are our prototype costs. So we just have 3 things that we purchased this semester. Fortunately for us, a lot of our materials were in the lab, so we didn't necessarily have to buy all of the components, but we do have a list of the cost of the microcontroller, the sensors we bought, and then our display board.
So now to talk about some of the lessons that we learned from this semester. Personally, for me, it was a great, at least starting point to understand what it takes to make a big picture project work. You have to do a lot more planning than I originally realized. Earlier group projects that I've always been a part of, there's always been, it's been a shorter time frame to be sure. So understanding the amount of organization and planning and communication that's required is probably the biggest thing that I've learned.
For me, again, building off what Trevor said, organization and planning is going to be very key going forward. But for me, what I've really learned is how to actually use the things I've learned in classes, like how to build a circuit and all that, and actually build a live working system. As well as I learned how to solder this semester, and I did enjoy it. Learning to solder. So.
Yeah, for me, I think the most important thing I learned is how to fully use the resources is available to me. Like for this semester, I learned the PCB, and I created the schematic of that, and I really I think it's really helped to me.
Yeah, several things that I learned this semester. I learned how to properly use a data sheet. Data sheets with all those numbers, I usually don't know where to look for, but now I know how to look for the appropriate values and what's appropriate for our project, for different designs. Soft skill that, I mean, every time you work in a team, you learn different things about teamwork, or you build on things about teamwork. Like Trevor and Austin said, communication is key. Communication with the sponsors, making sure the idea is clear, and then communication between teammates to make sure that we're on the same page and that we're on task.
I think for me, I haven't really coded much in the past just because of the nature of my major, but I actually did it a little this semester just with the LCD display that I was working on. So that was sort of nice to touch up on those skills from freshman year. And then on top of that, I think what was really important for me is that I'm a person who likes to just do everything at once. Like if I have an assignment, I'll like sit down for 8 hours if that's what it takes, but you can't really do that for this. And I think at the beginning, I really wanted to like force one specific thing, like the first thing I found, first idea there was, but helping our team breaking it up into smaller components, like I do the LCD, you do the power, that really helped me sort of not make the project so overwhelming. And I think that we sort of figured that out towards like the end of the semester, but I think that's really important going into next semester, just assigning those right away. And I think we've been doing a really good job with communication.
Yeah, so just in summary, wanted to give everyone a taste of where we're gonna go and our future plans for the semester, next semester rather. So, okay.
No, go ahead.
So this is just a overall summary of, you know, what we're planning to do again, and what we've accomplished. So we want to reduce hunting time and overall difficulties in terms of finding parking spots and surface lots, and displaying that to a user in a way that is feasible next semester. I think that's what will a big decision will be for us at some point, is figuring out what are the capabilities of the communication system that we're going to come up with. If cellular is an option, to send to a server and a website, or maybe there's no infrastructure on the lots, and you know, a gate, or not a gate, but an LCD display is maybe the best and most cost-effective way to do that. So again, just sort of in summary, that's the direction that we're heading into in terms of prototyping and final design for next semester. So thank you for listening to our presentation today. If anyone has any questions, please. Oh, yeah. The most important thing.
Yes.
So now we'd like to demonstrate to you our prototype and then afterwards open the floor to any questions.
Got it. I will do it again. Okay. No.
That's entering. It updates the count up.
Yep.
So
And do one more leaving.
Yep. Sure.
So this you enter, I exit.
But, okay.
Oh,
Same time.
Same time, yep.
I think it changed. Maybe.
oh, okay, you enter. I'm gonna exit before you enter. Okay, you don't miss the sun.
Yeah, be on the road, if we're looking at the distance.
Oh. Oh,
So it
I
counted up
counted.
and
Counted
it
down.
counted down.
you
So
see what
it
I did?
doesn't show that an object,
Okay,
it'll count the object once you leave.
leave. Oh.
So if
I
you
block
keep it, yeah, it'll stay at -2. Or it won't go continuously go down. There's the way to put it. Well, there's also the
is it a
refresh.
delay?
Yeah, there's a
Okay.
delay.
Okay.
So that's one of the things that we had to play around with
Uh-huh,
because of the reliability of these.
okay,
If you set the delay too high and you read in a bunch of values,
okay.
it'll sometimes say that it's less than the max range and then it'll detect an object.
Mhm.
So one of the downfalls of the $5 sensor.
Yeah, well, I'm not surprised.
Yeah.
Okay,
So what I was mentioning with the resolution of the one
Yeah.
sensor, it would be very beneficial and we would have very little error dividing the road in two.
Mhm.
So if we, right? So if we do, I think what you were trying to accomplish earlier.
It might have actually done that.
Did not change. Which is one come in, one goes out.
Right.
Right, yeah. It's like I wanted to block the sensor because so this one is 13 feet, right? But this one, for some reason, doesn't see that, or does it? How does your code work?
So,
Because this comes in,
yeah,
this one looks like it sees it, not
Yeah.
that one. How did you block? Did you put a limit to the sense?
yeah, that's
like,
how,
yeah.
so essentially there's like a max range, which is the midpoint of the road. And so if this is less than the midpoint of the road, essentially, then it counts. Honestly, I'm not sure why, because they operate independently of each other, so. I picked up my hand on this one, but. Yeah, I think the board's getting in the way.
Your hand is in
Yeah.
front of it.
Good.
Any question from the presentation or from this, we can ask him to, I think he's resetting it, right?
Yeah. Oh, whatever happened there.
Yeah, so algorithmically, you're looking for the distance from the sensor.
Yes,
So
so,
that's why this sensor wouldn't pick up over here.
yeah,
Is it because it's blocked or because you understand the distance?
so,
You know, is it because this can only read to here? So you have to position it, or do you understand that?
so it's reading past the point of the midpoint. But the way that it counts is looks for less than the
Gotcha,
midpoint.
yeah.
So it disregards anything, so that's why you have a second sensor on the other side.
Yep.
So. Yeah. So then this should go up. And that should go down. So I don't know what was going on before, but if there's two things in the way, it should have worked and it stays there. So. It can, I don't know what happened at one time, but it should work if they're coming and they're two in the way.
So you had level 2 and level 3,
Mhm.
what how are you changing this to level 2, level 3? What is level 2 and 3?
Should I turn this off?
Yeah,
So
yeah, thank you.
I think level 2 is gonna be
I can plug.
4 sensors and